Okay, guys, this has got to be one of my favorite sections. I know, I understand that I say that all the time, but I'm just going to do a bunch of examples for you about determining the radius and interval of convergence because it is so much fun to do. So let's do this. Come on. Come on. Come with me. Let's go. So determine. We're gonna do a couple, maybe three. Okay, couple is usually two, but the radius and interval of convergence. So you've read all about power series. They're your new favorite superheroes. They always sound like superheroes to me. Power series, right? Convergence of each power series. These are so much fun to do. It's just so much fun. Okay, so the first one I would like to do for you, and because you're forced to do what I want in this video, if you have decided, or if I have forced you to watch this video, let's look at this. Okay, all over the square root of, okay, so as you saw in the book, what we really want to utilize when we're doing these power series is the ratio or the root test. So basically when I'm asking you to find the radius and interval of convergence, what I want you to find is I want to find all these x values that if I put that value into this series would converge. That's what that's asking you to do. Because remember, x is just a real number, right? So I want you to find a real number that when I put that real number into here, this series will converge. And there's going to be more than one of them, usually. There might be an infinite number of them. Well, we could talk about countable or not countable, but let's not worry about that. Anyway, well, not even that. Well, I'm going to stop. Okay, so on this one, I'm going to go ahead and use the ratio test. I think the root test would be pretty easy to use as well. But I'm just going to go ahead and use the ratio test, okay, and let's do this. So remember the ratio test tells us to take, I don't think I want to do it in green though. Let's take the limit as k approaches infinity, right, of the absolute value. Now, I'm doing the ratio test. I know that I'm going to take the absolute value, so I'm going to get rid of that -1 because I know that it's going to go away anyway, all right? Now, it bothers me a little bit that I did that without actually kind of showing that step. You know what, you guys? I'm going to get over it. It's going to be fine. But I know I'm going to take that absolute value, so it's going to be okay. So I'm going to take the limit as k approaches infinity. See kind of what we have on top. I'm going to break up that x to the k plus 1. It's going to be x to the k times x to the 1, because remember, what do we do with exponents when we multiply like bases? That is right, folks. We add their exponents. So I'm basically undoing that addition. Right? And the whole reason I'm doing that is because now these guys cancel. So what do I have here that does not depend on k? It's that x, right? So I can actually pull that x out as an absolute value outside of the limit. Get out of here, x. And now I can take the limit as k approaches infinity. What is this? They're both under the square root and it's division, so I know I can put them together as long as it's multiplication or division. I don't even need the absolute value anymore because I know k starts at 1. It goes to infinity. I also know when I take the square root of it, it's a positive root. So as I look at what's happening here, this inside ratio right here, the k over k plus 1, that is going to 1, right? Because k divided by k, I just take their coefficients. That's the largest degree on top and bottom. I just get 1. What is the square root of 1? It's 1. So look at what I have here. I have absolute value of x times 1, which is just absolute value of x. So when I've done my ratio test, right, I have found that the limit of a sub n plus 1 divided by a sub k plus 1 divided by a sub k is the absolute value of x. When does a series converge under the ratio test? This is why we use the ratio and root test. I know it converges when when whatever my limit is less than 1. All right. So look at what we have. I have the absolute value of x is less than 1. That means that x must lie between -1 and 1, right? Can either be, if it's -1, well, we don't know about the ends yet, but that's what we know is the absolute value of x less than 1. That tells me I can be between -1 and 1. Now what you have to do when you're dealing with these is you have to test your endpoints because we're not sure about our endpoints. Remember, if x is equal to 1, right? In this case, if x is either 1 Or if x is -1, then what do I get? I just get 1. And remember, the ratio and root tests are inconclusive if our limit is 1. So we have to test. So what we're going to do, I always start with the smallest number. So I'm going to start with x equals -1. I'm going to take that -1. And remember, I'm asking what x values make this series converge or diverge. I know right now that as long as I pick an x value between -1 and 1, I'm guaranteed that the series will converge. What I need to know now is what about the endpoints? So I'm going to take these numbers and I'm going to plug them into my series here as the 1 and -1, and I'm going to see what happens at those endpoints, okay? Because we know that when it equals 1, it's inconclusive, which means we have to do something else. So this series, if I let x equal 1, right, I still have that -1 to the k. I'm going to have 1 to the k then, all over the square root of k. Now, 1 to the k is just going to be 1. So every time I put in a k value, k to anything other than infinity, right, that's an indeterminate form, but k to any number, and because k are discrete numbers, we're going through these numbers discretely, this is just going to be -1 to the k all over the square root of k. Now we're going to take everything we learned in chapter 10 and we're going to figure out, does this series converge or does it diverge? So let's look at a couple things here. First of all, this is an alternating series, right? So I first need to test for absolute convergence. Oops, sorry about that. Don't know, go away. Yeah, I know. Okay, so for absolute convergence, right, if the absolute value of this series, that's always what I want to kind of go for, is absolute convergence. But if you can see like right away that this is not going to be absolutely convergent or converge absolutely, I would just go ahead and go to your alternating series test and get there, right? So this guy is a divergent P series. So it's not, right? How do I know that? It's because P is equal to 1/2, which is less than 1. So what do we know here? It's not absolutely convergent, or it does not converge absolutely. That does not mean it's divergent though. So remember with the alternating series, right? We have absolute convergence, but then we also have conditional convergence, which is convergence, right? And so what am I going to go to do that? I'm going to do the alternating series test. Remember what the alternating series test tells me I need to show. Number 1, I need to show that it is a non-increasing series, and that's pretty easy to do because I know that the kth plus 1 term is less than the kth term, right? I don't even need to do the derivative or anything because I know that I have increased the denominator, and that makes it a smaller number. And then what was the other thing I needed? I needed the limit to go to 0 of the kth term as k goes to infinity. And sure enough, it does, right? So we're set. Okay, so what do I know about x equals -1? It does have conditional convergence. It passes the alternating series test. It converges. So I can come up here to my little thing here and I can put an or equal to. Because if f is negative, or if x is -1, I've shown that it converges conditionally, which is convergence, right? The conditional convergence, not a huge deal, but it is convergence. All right, now I have a feeling that when x is 1, it's not going to work. If x is just plain old 1, oh, I mixed those up, didn't I? Oh my goodness, Sarah. I'm so sorry. That was for x equals 1. Man, come on, Stan. Well, I say Stanley because that was my maiden name. So sometimes I call myself by my maiden name. It's fine. Don't worry about it. So anyway, so now I need to come back here. And I need to just, I need to put my or equal to, excuse me, with the 1 there. Now let's look at x equals -1. When I really get a little excited, I really enjoy this topic. So I was just super excited to record this lecture. All right, let's put in -1. When I put in -1, so I have the -1 to the k, right, from right here, okay? And now I'm going to have, instead of x to the k, I'm going to have -1 to the k, okay? I know, that was a stupid joke. I'm sorry I did that. There's no excuse. It's just, I don't know. All right, so what am I going to do here? Sometimes you got to think about this a little bit, and it's, guys, it's okay, and ladies, it's okay to think, right? So -1 to the k times -1 to the k, they both have the same exponents. So I know that this is -1 times -1 to the k. I can do that across addition and, or excuse me, I can't do that across addition and subtraction, but I can across multiplication and division. -1 times -1 is just 1, and then 1 to the k, that's just 1, right? As k gets, for whatever k values we put in. So what is this series going to do? This is just going to be 1 over root k. As we saw before, this diverges. Why does it diverge? Because we have a p series. You got to tell me why. We have a p series with p less than 1, and that's a divergent series. So as I look back up here at my possible interval and radius of convergence, let's do that right here. I'm going to keep that or equal to with the 1, but I'm not going to put an or equal to with the -1. So my interval of convergence, you're going to use interval notation. Right? I'm not going to include the -1, so it's an open parenthesis, and I'm going to take every x value up to 1, and then a closed parenthesis because it will converge when x is equal to 1. And what is my radius of convergence? As you saw before, my radius of convergence really is when you look at this step right here. Oh, whoops, actually I'm actually going to go this step right here. Once you rewrite it so that you have a 1 in front of the x term, even if you're adding and subtracting terms to x, that's okay. But once you get a 1 in front of the x term, you should have the same distance on both sides. So when you determine the radius of convergence, you need to make sure that these numbers have the same absolute value. And then you just take the absolute values of those numbers. And so in this case, what is my radius of convergence? My radius of convergence is 1. Okay, it's basically that distance I could go. I mean, you could just take the distance of the interval and divide it by 2. Okay, that would be your radius of convergence. Isn't that fun? For this section, I'm just going to do examples with, I think the hardest part is figuring out these intervals and radius of convergence. The rest of it in this section isn't too bad, I think. You know, when it talks about the binomial, or no, we're not to binomial series yet. When it talks about differentiation and functions and stuff, I think you can go through that. But what I would like to do is just talk about the radius and interval of convergence, because it can be a little bit tricky. All right, so let's look at something like this. I know this one's going to be a little bit short, but I want to look at something like this. So I have k times x minus 1 to the kth power. And again, I want to find x values that is going to make this converge. And maybe you can already look at it. Hopefully you can and see that this kid's going to have a tough time converging, right? I have this k in front of the x minus 1 to the k. That's really going to cause it to grow pretty fast, quickly. And then, you know, no matter what number I put in here, it's still going to grow fast. So my gut feeling is that I'm not going to have a very big interval of convergence. Remember, you always are going to have one of them. You have at least one term that'll make it converge. So let's go ahead and we'll just do the ratio test again. And then the next example, we'll do the root test. So I'm going to take the absolute value of the kth plus 1 term, right? And again, this power series now you can see is centered at 1 all over the kth term. All right, so this one is it's not simple, but it's a little bit faster than the other ones. So I have a k plus 1. I'm going to break off an x minus 1 term, right? Same trick that I did last time, all over k times x minus 1 to the k. And now these guys cancel. So notice what is left. I have x minus 1, the absolute value of that, times the limit as k approaches infinity of, oh, I was wrong. What? I was wrong? Of k plus 1. Oh, yeah, never mind. As long as this number right here, right, is a number less than 1, this guy's going to 0. So we'll be good. So this one's going to be pretty interesting. Thought I was going to do something else. I'm all right with this. This guy again goes to 1, right? I have k plus 1 over k. So this tricked me a little bit. So I have the absolute value of x minus 1 is less than 1. So this is a good example of one that is not centered at 0. So again, what does that absolute value mean? It means that I'm squished between -1 and 1, right? I want the absolute value of whatever my number is to be between -1 and 1. And again, at this step right here, this tells me that my radius of convergence is 1 because I have a 1 in front of the x term, right? And I have the same distance on both, the same number on both sides. Okay, but now I have to figure out what my interval is. So let's see what x, so I'm going to solve this inequality for this compound inequality for x, which means I'm going to add 1 to everything. So what's my possible interval of convergence? Well, it's going to be between, x needs to be between 0 and 2. Now I just need to check, can x be 0? Can x be 2? So let's check, I didn't mean to actually write check. Let's look at x equals 0. So my series then, I come up to my original series here, and I'm going to put in 0 for x. So it looks like I get the series k equals 0 to infinity. I don't think it's 0, it's 1 to infinity. Okay, and I'm going to put in 0. So I get k times -1 to the k. Guys, this isn't converging. How can you prove that for me? Take the limit, right, of the absolute value of this term right here, k, that equals infinity, which is not 0. So remember, this is technically an alternating series, but for an alternating series to converge, the absolute value of its kth term has to go to 0, right? That's the second part of the alternating series test. So if you can just see that without that negative, it doesn't go to 0, we know it diverges. So poor 0, 0 is not invited to this party. So I'm not going to include 0. What about x equals 2? So I would get k equals 1 to infinity of k times 2 minus 1 is 1. So this is 1 to the k. But 1 to the k in terms of our series here, because we're not taking limits, is just 1. Again, how do I know this guy? This guy's going to diverge. I mean, we're taking 1 plus 2 plus 3 plus 4, right? That guy's never slowing down. But I need to justify my answer. And remember, that's the divergence test. The divergence test says if the limit of your kth term is not 0, then it diverges. Doesn't say that it converges. It just says for sure it diverges. So I'm not going to include either one of the endpoints. This guy is not going to converge with any of the endpoints. So what is my interval of convergence, or the IC, if you're cool? It's 0 to 2. What is my radius? It is 1. And sure enough, it's 1 because if you took the length of the interval, 0 to 2, that distance, of course, is 2. And if you divide it by 2, right, cut it in half, what's the distance you would have on both sides of that midpoint? It would be 1, if that makes sense. All right, let's look at one more example and then we'll call it good because we're already at 18 minutes. Okay, so how about this one? Again, oh, I kind of messed up my numbering. I think this should be like C or something. But, oh, that should be a 0. Okay, let's look at k squared. X to the 2k all over, what do I got here? K! Also known as k factorial. All right, so let's do the ratio test again. Sorry, I meant to do one with a root test, but look at the examples, look at the fun sheet. They'll show you all that. I got to do the ratio test kind of on this one because of that k factorial. All right, so if we do the ratio test, so here's where you got to be careful. Let me tell you something. 2k plus 1 is not the same as 2 times k plus 1, okay? Okay, it is. Parentheses are important. I'm pretty sure if you've watched my videos, I've said that about 100 times. I shouldn't throw out numbers there without actually knowing, but parentheses are important. You have to replace, whoa, settle down there, Sarah. You have to replace that k with k plus 1, so you must use parentheses. Yes, I will mark off if you do not. All right, everything, I'll mark off, guys, because it's wrong. You're wrong. Sorry, it's wrong. All right, I take the kth plus 1 term, I divide by the kth term, so dividing by a fraction flips it good, and then we multiply. And now we have a little bit of work to do, but this one I think you'll see is going to end up pretty nice. So now I have the limit as k approaches infinity. I'm going to start messing with this a little bit. This is still k plus 1. squared, but that x to the 2k plus 1, that's x to the 2k plus 2, right? If I take that 2 through for the correct way, and then I can rewrite that, I can break that up as x to the 2k times x squared. And I also have a k factorial on top, because with fractions I just multiply straight across. With that k plus 1 factorial, I'm going to pull one of the k plus 1's off, make that x, that k factorial. And then what else do I have? I have a k squared, and then an x to the 2k. And now, this is the fun part. I love doing this. I just start canceling. So the x to the 2k's are gone. The k factorials are gone. Even one of the k plus 1's are gone. That x squared does not depend on k, so I'm going to bring that out. I technically don't need the absolute values, you guys, because anytime I square something, even if it's negative, it becomes positive. So I'm not going to worry about, put it. It's not wrong to put it. And then I have k plus 1 all over k squared. This is where it just got interesting, right? Because look at what, and I don't need the absolute values either. I know that k is positive, but look at what's happening to this. The degree of my denominator is larger than the degree of my numerator. So you guys, the sucker, it's going to 0. Hey, so what does that mean? Well, that means that this guy is less than 1 for all values of x. No matter what I put in for this x squared term here, you guys, guess what it's getting multiplied by? It's multiplied by 0. Guess what your answer is always going to be? It's always going to be 0, no matter what. No matter what x value you choose, it's always going to go to 0. So up here, basically what's happening is that no matter what x value I chose, this k factorial in the denominator is just growing so incredibly fast that eventually it's going to cause that series to converge, okay? So that is for all x. So these are kind of my favorite, because who's invited to the party? Everybody. You're invited and you're invited. Everyone's invited. What's my radius of convergence? Infinity, right? Because clearly infinity plus infinity divided by 2 is infinity. That's pretty bad. All right, guys, these are so much fun. Work on them. There's a lot to do. I get it, but practice, 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 and ask me if you have any questions.